please.
Okay, so questions for you now. In one simple case, you can make an easy identification of the likelihood ratio with the chi-square. Shall I bring up the equations again or not? Anybody? So let me ask you a question and to bring you on the right track. What happens if your likelihood, it's not a multivariate Gaussian, it's something else? The chi-square is still this big. Is one, x per 2 the other, minus 2 the other one? So what he's saying is, let's see if everybody agrees, is that if this thing is a different beast, it's not a multivariate Gaussian, right? And you still insist in using the chi-square, you would be insisting that your likelihood looks something like this. So you will be forcing your likelihood to be something close to a Gaussian. Can you spot another difference here? Which I know Antonio spotted because he told me before I actually did that this question. So Antonio, you cannot reply. Shall I give you a hint? This bit, which is the same bit that is here to the minus 1, right? You take a chi-square that's completely ignored. So, in some cases, the errors don't depend on the parameter you're trying to estimate. But typically, when you are dominated by the noise of your instrument, if the noise of your instrument doesn't depend on what's out there in the sky, then that will be the case. However, in some other cases, this bit may actually depend on the parameter you're trying to estimate. Typical example, the cosmic microwave background, you approximate it to be something close to a Gaussian, okay? Then you compress this in CL, and then you write your covariance wherever. That covariance does depend on the parameters. That's exactly why you need CAM or class to compute your CLs. So if that bit depends on the parameter you're trying to estimate, then you can't forget this step. And indeed, if you do in the cosmic microwave diagram, you'll find bias also by forgetting that detail. So when people do the analysis of large scale structure, we have seen the presentation today about EAO, they do ignore this bit here. Now the questions for those who are going to do that exercise is why? And does it matter? Okay, so let me go on and say, okay, you want to do confidence interval, so visually, if that's your distribution, you want to cut it in such a way that you have 68% in here, so 34 and 34, or if you want 95%, you cut it more. Let me go on. Now, that is fine if everything is Gaussian. But I want us to be a little bit more realistic. And unfortunately, when we apply to data, we need to take a trip back in time. And we'll see why from first principle. I don't know if today or tomorrow. So, when you want to report error confidence interval region, you need to ask yourself what errors. So, if the prescription is this, and everything is Gaussian, then it's obvious. You say, well, you know, I sit on the maximum, which corresponds to the mean, and then I cut around until I get to the required level. However, think of an histogram and think that you have a distribution that looks like that. And I'll give you an example, for example, with the redshift. The probability of the redshift, that there are two peaks, one a very low redshift and one a very high redshift. And this is, you know, an idealized case like that. Then you can think of several different ways of reporting your confidence region around. You can say, oh, well, I can sit around the median, and then I can give an equally tailed interval. So I integrate here and I integrate there until I get to 34 plus 34, okay. Or you can sit on the maximum and say, well, let me now go down in the posterior until I get to a level so that when I integrate down, and you can decide whether you're going to do it continuous or discrete, in this case, the maxima, I reach a given level. And in this case, it doesn't need to be symmetric, because it's just, you know, taking a water level. I lower the water level, then this comes out and this comes out until when I integrate from here to there, I get the required number. Or you can do the same, but centered on the mean. And centering on the mean is actually what a lot of this publicly available code spit out. CosmoStatistics and all that spits out something like that centered on the mean. Now, for CMB data and for blank, it's not a big issue, but we have seen for photometric redshift it actually makes absolutely no sense, because in the example there, the galaxy was either a low redshift or a high redshift, but not in the middle. So reporting this in that context will make no sense. So, the exercise for you is to see this for yourself. And that's why we need to do step back in time. So you want to get the histogram for the effective number of neutrino species that came from W19 data plus the VAO that were available back then, 2011. So these are obtained from the posterior, from many other parameters that I've already done the job for you, and I gave you just the histogram. And in that Dropbox folder or the folder that is linked to the web page, you should find this file. And I want you to report the Bayesian central confidence interval, that is the mean and then symmetric, 34% left, 34% right. And then the minimum, what is called the minimum Bayesian confidence interval, if you take the maximum of the posterior and then select a contiguous region so that in this contiguous region the posterior is above a given threshold and you still integrate that 68% and 95%. So I give you a few minutes to try to do that. the exercise because we didn't have the first 5 lectures already. Then you can continue on at your leisure. But if you know how to program and how to read a file and things like that, I give you a few minutes to try it out. You should probably move on, and if you haven't got the confidence level, the confidence regions, I'm sure you will have time in the afternoon to finish that up. Let me show you the result from a paper that came out in 2007 discussing exactly this issue. Okay? Okay, so this is the paper. This is a slightly different data set, but the same concept. You would recognize this looks a lot like the distribution we plotted. Obviously, mean and central symmetrized confidence region around the mean is not the same as this one. Forget about this one, that was a different point. So what the codes out of the box, CosmoMC, etc. spits out is this one, other code may spit out this one, and I would argue that this is more reasonable to record than this. Alright? Now you did that in 1 dimension. You may do that also in 2 dimension. So if you want to do it in 2 dimension, there are histogram files also for doing that. This is Hubble constant versus the signed horizon radiation drag for the actual Planck data, 2015. But without using the high-end polarization. And now we go back later on why I didn't use the polarization. Or you can plot the number of effective neutrino species versus the standard horizon radiation drag. That's the one. Again, without using enough polarization. So this standard horizon radiation drag, as you have seen, it's a crucial quantity to interpret baryonic acoustic oscillation data. So it would be good to see what the cosmic background tells you about this quantity, about this standard ruler. First time. So if you want to take a look at the file, make sure you can open it and at least plot them. And then the integrals, you can do them in your own time. Because before it was 1-dimensional integral, now it's a 2-dimensional one. So it depends how confident you are with this sort of integral. So you should be doing it here. So the file begins with the x values of the histogram, so the x.
The HO is the first one?
Yes.
And what is this sun horizon navigation drag?
So first you have all the value for the first variable, then you have all the value for the second variable, and then you have a big cube, which is the size of first variable times size of second variable. So that's the way the file is. So let me go on and introduce the last concept that I want to do this morning, and then I will be available to help you for this 2-dimension. Okay. So the next concept that I want to introduce today is marginalization, which you heard about already, and nuisance parameter. Two are obviously related, and it will be obvious in a second why. So, what are nuisance parameters? Who has heard about nuisance parameters before? Who has ever tried to, open the blank result explanatory document? Okay, we'll come back to this later on because it's one of the things that I will ask you to do. Just open them. So imagine you're analyzing the plant data, and what you want to know from the plant data obviously is omega lambda, is there a quintessence, what's omega matter, but in order to get there, right, you don't see the cosmomagnetic diagram in the primary in its full glory. You see it through the emission of our own galaxy. So you have somehow to subtract the emission at those wavelengths of our own galaxy. And so obviously the parameter that describe the emission of the galaxies need to be taken into account. Otherwise, if you fix them or if you just put them to zero, you will get the wrong result. But at the end of the day, these are parameters that are interesting mostly for the Planck team people. They're not interesting for you, right? Unless you're interested in galactic structure and you like to study dust and what dust does, where there are magnetic field and things like that. So for you, all those parameters that describe the properties of the foregrounds are nuisance parameters. They got to be there, but you want to get rid of them somehow. They need to be accounted for, but you don't want to see them. So that concept of nuisance parameter. And marginalization comes in handy because what you want to do, you want to have the posterior for the parameter you're interested in, marginalized over all the nuisance parameters. So that's where marginalization comes in. So when you marginalize, what you want to do is, well, if you have a posterior for vector of parameter alpha 1 to alpha j, and you would have extra parameter that goes from j plus 1 to m, which are the uninteresting one, you take your full posterior, which depend on alpha from 1 to m, and then integrate it over all the parameters you don't care about. You don't fix them. If you fix them, you're going to get wrong answer. You have to marginalize them. So the alpha are all the parameters. That's the full vector that goes from 1 to n. The one you are interested in are the one that go from 1 to j. And the one that go from j plus 1 to n are the one somebody else is care but you don't. And so that's this is a typical example you may find yourself dealing with. That's one parameter, that's the other parameter. Let's say you want to marginalize over this parameter because this is the uninteresting one. Once you marginalize, of course, you will find some strange behavior, right? If everything is Gaussian, then this operation is relatively simple. When things are non-Gaussian, then all sorts of things can start to happen. But marginalization this way is the correct thing to do, because you want to know what your probability distribution for the parameter you are interested in is, regardless of the value of the nuisance parameter. So this regardless of the value of the nuisance parameter means summing all the possible value of the nuisance parameters with that way, which is what the marginalization is. So before going on and trying to do that firsthand, I want to show you some useful tricks for Gaussian likelihood. So let's say you know that you have a multivariate Gaussian. And let's say that you want to marginalize over a poorly known point source sampling. This does happen in reality. That's one of those that you may call nuisance parameter. because the point sources may be very interesting for people that study extragalactic stuff, but if you are interested in the cosmic diagram primordial parameters, these are the problem for somebody else, so you may want to marginalize on that. But it turns out that if you know that everything is a multivariate Gaussian, so these are your CLs, that's the data, that's your theory, that's your covariance matrix, and that's the prior you may have on the amplitude of this extra contribution from point sources. You can do it on a loop. So what's behind this square is the solution. Now, what I ask you is whether you want to see the solution or whether you want to try. You want to try? Shall I tell you a hint on how to find the solution? So the hint is to recognize that here you have the typical Gaussian integral, and here you can break this up with something that looks a lot like a Gaussian integral, right? You could have to integrate over a term constant for A, a term linear in A, and a term quadratic in A, and here you have a term quadratic in A. And then you go and you look either in Mathematica, MATLAB, or in one of these big books of integrals, and you would find that when you have to integrate something that has e to the constant term, this linear term plus quadratic term, the solution is blocked. Do you want to try, or do you want to see the block solution? Let me show you the solution, and then you can actually work out if you're rewriting this in terms of constant term, linear term in A, and quadratic term in A. That's the solution. The solution, the trick is to recognize that this integral can be written as, when you integrate in A constant, a linear term, and a quadratic term, and then you do this substitution, and as this substitution you realize, this is a Gaussian integral, so this is the result. And you can also think of other cases as well. So imagine that instead of having an additional term with an A in front, you have an amplitude in front of your theory and some prior of an amplitude. And this also has an analytic solution. Okay. Alright, so instead of doing this exercise, which I can leave there for you, the exercise for you would be, once you manage to extract that 2D unaffected versus sound horizon or H0 versus I horizon, marginalize one parameter with respect to the other one and compute the marginalized.
The graph is an erosion. The graph of the H0 versus the second. But is an erosion.
It should be a two-dimensional thing. Right, we have H0 and RS, and then you should have like a mountain here, which is your posterior. And that posterior should not be a nice spherical hole because of the quantity are controlled. Okay, so we're not going to do it with this one, but what I want to ask you to do is go to the Planck wiki that explains you what the Planck library this, because probably you would use some of this data to do some of the alignments, or at least you would use the public checkings. And figure out how many nuisance parameters they actually have. Somebody is already smiling. In a land CDM-based model, how many parameters get marginalized over when a 1D log is shown? And for those of you who do the BAO things, this is one particular reference, but most BAO analysis that use the correlation function do this. How many nuisance parameters do they have at the moment of fitting? How many interesting parameters do they have? The bottom line of this is that sometimes you may have more nuisance parameters than actually interesting parameters. So it's good to know how to marginalize, and also it's good to realize that if you have to do highly dimensional integrals, you may want to find something a little bit smarter than what I gave you to the marginalization. With multidimensional integral, it's a mess. So you can't do it with it, especially with these things. And